Our last speaker of this session is Dr. Butler. He is a senior scientist and chief of the geohydrology section of the Kansas Geological Survey at the University of Kansas, where he has worked since 1986. He holds a BS in geology from the College of William and Mary, an MS and PhD in applied hydrogeology from Stanford University. His current research interests include the development of field methodologies for site characterization, interpretation of water level fluctuations in monitoring wells, and the development of approaches for assessing and the sustainability of aquifers supporting irrigated agriculture. Jim was the 2007 Darcy Distinguished Lecturer of the National Groundwater Association. For those of you who have no idea what that is, it's an enormous honor and responsibility. You travel across the country, indeed across the world, giving lectures at institutions where you've been invited. He's also a recipient of the Pioneers in Groundwater Award of the Environmental and Water Resources Institute of the American Society of Civil Engineers. Dr. Butler?
Okay, thanks, George. And Kim, I was seated at a table with Kim, and she has informed me that I need to keep it short because there's a break coming right up. So I'll try to do that. But what I'd like to do is give you all an overview of some work that my colleagues and I have been doing to try to assess what are the prospects for attaining more sustainable conditions in aquifers that are heavily utilized for irrigated agriculture. Now, I'm from Kansas, so I'm going to focus on the High Plains aquifer. But I think the approach that I'll discuss does have bearing on other systems throughout the world. One of the basic messages that I'll try to get across is we can say a lot about these systems if we have the data. Okay? Okay, let's get rolling. High Plains aquifer. I don't think I need to say a whole lot about it. I think most folks realize this aquifer is of global importance because of the agricultural production that its waters support. I'm going to focus in on Kansas. Shown here in the inset, the tan area is the High Plains aquifer in Kansas. This is a critically important resource for us. In terms of irrigation water, 90% approximately of all the water used for irrigation in Kansas comes from the High Plains aquifer. We're heavily utilizing this system. This is nothing new. We've been doing this for decades, okay? And that heavy utilization has come at a price. And Lenny showed one figure on that. I'll just blow it up for Kansas. And this inset right center shows the portion of the state I'm going to be looking at. What I've got here is a map of the percent decline in saturated thickness or aquifer thickness since pre-development, since the onset of large-scale pumping for irrigation, which in Kansas would be approximately 1950, okay? The colors here, blues, mean an increase in aquifer thickness since pre-development. All the other colors are various degrees of decrease. Now, I should note here that these blues in the western portion of the state, those are areas of very thin saturated thickness from the onsets and from pre-development, so don't give those much significance. They're not of economic significance. But when you look at this map, you can see there are two tales to tell about the High Plains aquifer in Kansas. Notice in south central Kansas here, this area is under stress, but it's doing reasonably well. This is a subhumid area, and you can see from the yellows and blues, the preponderance of those colors, that the aquifer has fared reasonably well in the face of this heavy utilization. But as we move west, into the western third of the state. It's semi-arid in climatic conditions, and you can see the preponderance of reds, with the darkest red indicating that we have depleted over 60% of the aquifer since large-scale irrigation pumping began. And obviously, this is of great concern for us. And lots of issues, lots of questions about how can we moderate the rate of decline in this system? Is there the potential to achieve a sustainable system in the western third of the state? Now, when we talk of sustainability in the western third of Kansas, we have to be realistic. The best we can hope for is to do no further harm. In other words, the best we can hope for is stable water levels. This aquifer is not coming back, okay? What we want to do is see if we can't come close to stabilizing it. And then last, I would say 5-6 years in Kansas, the Water Management Agency, working with the stakeholder community, has developed some new management options. And basically, this allows groups of irrigators to come together to reduce pumping in the area, in a particular area, because obviously, if you're going to decrease the rate of decline, you have to reduce pumping. So then the question becomes, how much pumping do we need to reduce? What sort of pumping reduction will lead to a real change in terms of rate of declines, et cetera? So the irrigation community in Kansas turns to us at the Kansas Survey to address those questions. Now, typically, as groundwater hydrologists, we would turn to the distributed parameter flow model to get at that. Now, the problem is that's a very time-consuming, very data-intensive activity. So not particularly well-suited for nimble responses to queries from the stakeholder community about what happens in a 200 or 300 square kilometer area if we reduce pumping. So my colleagues and I have gone off in a different direction, and that's what I'm going to talk about today. We've come up with a different approach that exploits some of the data sources that we have in Kansas to, we've developed a simple, I would say, data-based approach with strong theoretical foundations that I'm going to explain here. Now, we pay a price for that. We have to rein in our aspirations in terms of the resolution of the assessment. In a distributed parameter flow model and groundwater hydrology developed by Dr. Pender and others over the years, we could look at conditions every few to several square kilometers. However, with this approach that I'm going to describe here, we're going to back off. We're going to be talking about conditions on several hundred, a few to hundreds square kilometers, even larger, into thousands of square kilometers. These are the size of the areas that we're getting questions about. And so we're focusing in on that scale. Now, I'm going to now talk about the data sets that support the method that we've developed, and then I'll go into the method itself and then come up with an example to show you how it applies to Kansas. Now, there are two data sets that should be the mainstays of any investigation of groundwater depletion. And I'm going to talk about what we have in Kansas in that regard. First, water level change data. Now, every year in the first week to 10 days of January, the Kansas Geological Survey and the Division of Water Resources of the Kansas Department of Agriculture, we send out teams, go across the High Plains Aquifer, measure water levels in a network of approximately 1,400 wells. Now, we do that in January, which is 3 to 4 months after the cessation of irrigation pumping, because the water level measurement at that time is going to be relatively insensitive to the year-to-year variations in the timing of the irrigation season, okay? The network that we have here was designed to give us a fairly even distribution of data points across the High Plains Aquifer, but we're using current or previous irrigation wells or former irrigation wells, so we do not have that exact ideal distribution, but it's pretty decent. Now, the Kansas Geological Survey has been in charge of this program since '96. Previously, the USGS was heavily involved in the program as well. The bottom line is we have data that go back decades in terms of water level changes. So very critically important source of data. However, the water level change is just the response element of an excitation-response relationship. We also need that excitation, which is pumping. Kansas, we're in pretty good shape in that regard because my predecessors in the Kansas water resources community had the insight to understand that we need information about pumping. So every non-domestic pumping well in the state now has to have a totalizing flow meter. Now, the transition to these totalizing flow meters has taken some time. 2013, the USDA did a survey of all the states. And at that point, 89% of the pumping wells, non-domestic, in Kansas had totalizing flow meters. Okay? The US, and I'd say now it's probably close to mid to upper 90s. The US average is 28%. Okay? And only 4 states in the nation have percentages greater than 40%. We need to do a better job in this regard, okay? So we said, let's take advantage of these data that we have. And how are we going to do that? Well, let me just go over this real quickly. The previous speakers have done an excellent job here in setting me up. We're just going to do an aquifer water balance, very simple. A water volume change is equal to inflows minus outflows. We're going to rewrite this as net inflow, which is everything coming in minus everything going out, save pumping minus pumping. Now, this net inflow is the same as the capture term that the previous speakers have talked about. So obviously, this is a critically important element of the water balance in terms of sustainability. You could see, set that water volume change is equal to 0, pumping equals net inflow or capture. We need to be able to calculate that net inflow term if we're going to be able to talk to the irrigation community about the impacts of pumping reductions. So how do we get at that? Well, we can rewrite that equation in common terminology, standard terminology for groundwater hydrology. Well, delta WL is the average water level change over an area. SY is specific yield, basically drainable porosity. I is this net inflow or capture term. Q is pumping. Divide through by area times specific yield. Get this equation here. Now, when we're talking about assessments over a few hundred to thousands of square kilometers, the specific yield is not going to change much in time as long as we're in the same aquifer. And what we've discovered is this net inflow or capture term in Kansas does not change much in time. So we can approximate this equation, assuming that this term, I area times specific yield, is a constant, and that 1 over area times specific yield is a constant. Then we can plot this change, average change in water level, and I'm dealing in respect to an earlier question, annual time frame here. So annual average change in water level over an area, plot it versus the total pumping, annual pumping. Look at the intercept and slope of that relationship and can calculate the pumping that would lead to stable water levels is just the intercept over the slope. And that's the same as the net inflow or capture term. And the key aspect here is prospects for sustainability are a function of the magnitude of this Q-stable term relative to the average annual pumping in an area, okay? Also, if we deem the Q-stable too difficult to attain, we can say, okay, let's say we're going to limit our losses. We're going to have a goal for water level declines of a few to several centimeters annual declines in an area, then we can calculate that the pumping that would produce that, again, from the slope and intercept terms. Okay? Now, I'm going to apply this approach to western Kansas. And I'm not going to go into details here, or we'll be even further delayed for the break. But suffice it to say, Kansas, we've got these groundwater management districts that overlay the High Plains Aquifer. They work with the State Water Agency to manage the groundwater resources. I'm going to focus in on northwest Kansas, Groundwater Management District 4. And I'm going to look, this area is 12,600 square kilometers. And I'm going to use data from 181 wells that were measured every year from 96 to present, and 4,242 irrigation wells with flow meters. So I'm going to plot these quantities against one another here. So again, the y-axis here is the average annual water level change from 181 wells. X is annual water use in 10 to the 9th cubic meters from over 4,200 irrigation wells. Each point here is a year. It's the year of lowest pumping was 2009, greatest 2012, 2014 there. R squared 0.77. So a reasonable job in terms of approximation of a straight line relationship. Note I'm not plotting 2006 and 7. Reason is we got a huge snowstorm in late December of 2006. We could not get in to measure the water levels. We couldn't finish it up until early April. So I've left out those years, 2 years, because they wouldn't be at the 12-month, approximate 12-month interval as all the other points shown here. So we could take the slope and intercept of this line and move forward looking at potential for sustainability. I'm going to do that graphically. So we can take the average pumping from 96 to present, and that turns out to be 0.53 times 10 to the 9th cubic meters, and that equates in terms of water level decline to 18 centimeters every year. So over this 20-year period, we've lost over 3.6 meters of aquifer, and frankly, in northwest Kansas, we don't have that many increments of 3.6 meters to lose. So what can we do to get to a more sustainable condition? Well, graphically, we just slide up this curve to get to 0 there in terms of the water level change. The net inflow turns out to be 0.41, 10 to the 9th cubic meters. That's a 23% reduction. 95% confidence intervals, like 15 to 29% reduction here. So this is practically feasible. The irrigation community can do this. They can drop it down 23% by using water more efficiently. Okay? This is something that's doable. And if they had, what this graph is telling us is if from 96 to now, the average annual water use in northwest Kansas been 22 to 23% less than actual, the water levels on average would not have changed across this area. So there's reason for hope. One of the problems, however, is we don't know all the components of this capture or net inflow term. So if irrigation return flow is one of the components, we would expect that to be decreasing with time. So if that decreases with time, what we're going to see is a shift downward of this plot. And if it decreases by a factor of 2, we're going to get to this dashed line here. And then the potential to get to sustainability is much less likely. It's a much more arduous task for the irrigation community at this point. But what we've got here is this simple approach. If we have the data, we can get at this net inflow or capture term. We can also monitor its changes with time. Okay, we'll be able to pick up as it slides it slides down if that occurs. So very quickly, in conclusion, in terms of what are the future prospects in the High Plains Aquifer in Kansas, out west from northwest Kansas and lower to mid-20s reductions would give us stable water levels. As we go down into southwest, more heavily pumped southwest Kansas, we're talking about mid-30s. South central Kansas, it's much more better prepared for this. Just few to several percent decreases in average annual pumping would lead to stable water levels under current climatic conditions. So the key here, we can say a lot if we have the data. So I'll end there just with some acknowledgement of funding sources. Thanks.
So we'll take a couple of questions, please.
Hi, my name is Peter Huyakon. I'm very impressed by the presentation by Lenny and you, James Butler. I saw in the last slide, Lenny mentioned the word management optimization. I'd like to expand on that. The approach that you have outlined, Jim, is a very good order balance approach. But I think in view of the data that you have collected, technology now exists for you to incorporate that in an integrate distributed model that could be combined with management optimization so that you can pose a very formal objective function, decision variables, and constraints. In fact, technology now exists for you to combine these with physically based model and run it on the cloud system. And I think this is something that needs to be recognized because while we're all trying to make decisions using simplistic approach, the number of decision variables and constraints are beyond human brain to figure out what to do. So I think in the future, I would encourage the use of engineering solutions that Melanie talked about with the well-invested development of distributed model and run it in conjunction with the management optimization approach. You've got vast amount of data. And I've seen also the presentation by Dr. Bridget Scallon that talk about large-scale models. One of the concerns I have when you do modeling is quantification of uncertainties. When you calibrate model, you try to predict it. You need to have somewhat means to quantify the confidence level of your model prediction. So that is another topic that needs to be addressed, and I hope that we can emphasize this more in the future. But I do believe and have confidence that technology now exists, can be combined with the new evolution of the cloud-based system that allow you to simulate using formal objective function, using thousands of simulations that can be done on the clouds using multiple CPUs that can give you the result that can be analyzed in a very effective manner.
Thank you, Peter.
Well,
that's my comment, so I hope that...
Okay, and that takes me back to my MS and PhD advisor, Erwin Rimpson, who was a huge fan of optimization modeling, one of the early guys in groundwater hydrology. We just came up with this method within the last 2 years, and so certainly we and others will be exploring things in more detail in the future. The key thing we have to remember about distributed parameter modeling, we've got a lot of data here, but still it's going to be insufficient in many contexts. The model conceptualization issue arises and can be a challenge. But I agree with you, let's not stop here. Let's aspire to do more.
Another question? over here?
I'm Lynn Oscar with the National Academy. Could you talk a little bit more about how you can engineer capture? I mean, you're going to have big flood basins. What do you do to engineer capture?
We don't have much water to use in terms of aquifer recharge. One of the points I didn't make is, you notice on these maps, got all these blue lines here. That's wishful thinking. We have captured all of the surface water that there is to be captured out there through the development. So I'm not sure there's much we can do in terms of engineering capture. We've basically put the system in a world of hurt, and you know, that's just the way it is. So our efforts have got to be focused on reductions in pumping.
One more question?
I've enjoyed, I guess I should say, my name is Oso Asare from Penn State University. I've enjoyed all the presentations, and I'm reminded of, in the academy yesterday, there was a session on seawater rise, and I'm sitting here thinking, so what's the problem? We have more water in the oceans, and we are depleting water in the mainlands. Why don't we just practice desalination? I'm just thinking as a child.
Would you like to speak as a parent?
Well, hey, I mean, in Kansas, the oceans are underground, okay? So there has been a move by folks in southwestern Kansas to take water from the Missouri River, so-called excess flows from the Missouri, and ship them out and use them to grow corn. That's still being discussed now, and we're looking for support from the American taxpayers.
All right, I think we're
Yeah,
gonna...
just a quick question. Peter Bethel from Cardno and also NAE, you said that you started monitoring all the pumping holes, water level in the holes in January each year. How well does that data correlate with your model's estimation of depletion?
Well, our models of depletion are based on that data. So it's a very strong correlation. Yeah.
So this is not the end of the story, but it's the end for now. We have to take our break, and we're down to 15 minutes. And let's do that, and we will invite additional questions later on in the program.